Hello everyone, this is Puya. In this video, I'll be talking about hashing. So before I start talking about hashing, let me introduce a new abstract data type called dictionary. Very briefly, uh, a dictionary abstract data type models a searchable collection of key element items. So every element in a dictionary would have a pair of keys and elements. This is a data structure for storing items indexed using keys, and this abstract data type supports operations like insertion, searching, and deletion. Its application can be in compilers for having a table of symbols of variables, and in memory management tables in operating systems and in larger scale distributed systems. Some common notation used for dictionary abstract data type is U for universe of all possible keys, right? So like a set of all possible keys, and K, which is going to be set of keys that are actually stored in the dictionary. So it's basically K is a subset of U, and the number of elements that are stored in K is usually known as N. So one way of implementing it might be using arrays, but when U is a very large set, arrays are not practical because all these operations are not going to be done efficiently: insertion, searching, and deletion. So a solution would be another concept called hash table. So a hash table is an effective data structure for dictionaries. In the worst case, search in a hash table, it's going to be in a time complexity of O(n), but the average time complexity we're trying to reach a constant time, so order of 1. So that's expected time or average time for search in a dictionary. Some of the methods or member functions that you can design for a dictionary abstract data type would be finding an element, inserting, erasing, finding the beginning and end of the dictionary, and finding the size, and finding if your dictionary is empty or full. This shows an example. We're talking about key element pairs. So here, let's say like this is the student number, which is used as the key, and this is the string, so this is the key element pair. The space that's used is going to be order of n. The time complexity on the average, it's going to be on the order of 1. Okay, in the worst case, it's going to be also order of n, but on the average, time complex is going to be order of 1. Now let's talk about different methods for searching. We've already seen linear search or sequential search through arrays or vectors, and we saw that this is not very effective, but it works on unordered or unsorted structures. Its time complexities of order n. We also saw different structured or ordered searching. So for example, like we saw like binary search tree, like search tree methods. So it's done through using key comparison. Its time complexity, its order of the height, or it can be order of log n, right? If we have a complete balanced tree. And this is very similar to applying binary search for an array or vector. The advantage is that searching can be made much more efficient. The disadvantage is that updating the database is much more complicated and has the potential for disrupting the search process. Consequently, correct implementation is more difficult. We saw all about this when we talked about BST, balanced search tree, and we saw how difficult it was to insert or delete items from a BST when the property is violated, and we have to do some resolution for that. So I have to apply some strategies to maintain the properties of BST or AVL or heap or like any ordered or partially ordered or fully ordered structure. So what we are trying to reach is trying to reach direct access using key value. So like we want to basically assign a key value to every element so that we can do searching ideally in order of one. Okay, so the process for doing so, it's called hashing. So it's a completely different approach which does not depend on being able to sort the database records. So in this approach, our structure doesn't need to be sorted, but does provide structure to improve the efficiency of searches. Okay, so like it improves the efficiency of searching. The hashing methods are like, and hash functions like would basically give us an expected time on average time for searching of order one. For many applications, it is possible to trade memory for speed. So one way that we can reach this faster searching, insertion or deletion is basically to have a compromise between memory for speed. So like we have like more memory, more auxiliary memory to reach faster operation. An example was like you saw that like through merge sort, like we could reach like order of n log n for sorting when we used not in place sorting algorithm like merge sort. So the same thing can be applied for searching. So additional storage can allow for a more efficient, time efficient algorithm. So this is a trade-off between memory and speed. So now what is hashing? Hashing is the process of mapping a key value to a position in a table. So all the items that we have that we want to map, that we want to search through, or like we want to insert or we want to delete, they have a key value, right? So hashing is the process of mapping a key value to a position in a table. So like we basically, the key values, they can have any range. It can be integers, can be double, it can be characters. Like, so we try to map them to an integer number which represent a position in a table. This enables access to table items in time that's relatively constant regardless of their location. The function that does this mapping is called hash function. So it maps key values to positions in a table or in an array. Right? Each item ends up having a unique key. Okay, so this is what is ideal. Like we want to have like a unique key for each item, right? So a hash table is a data structure that associates keys with values, and the term hash comes by way of analogy with its standard meaning in the physical world, which means chop and mix. Okay. In hashed search, key through algorithmic function determines the location of data. So like we have a function called hash function that through an algorithm, right, through like a function, it determines the location of data. Then the transform key into index that contains data that need to be located. Hashing is a key to address mapping process. The implementation of hash table is called hashing, and hashing is a technique used for performing insertions, deletions, and searching, finding in constant average time. This is like what's expected, right? Average. constant time. And the operations, as mentioned earlier, insertion, searching, and deleting, and we also want to initialize the table, right? So like we want to initialize. This shows some example of hashing through um, figures. So here you see that like we have a universe of key. This is the actual set of the keys that we have for the problem that we want to program, right? So these are different keys for the items that we have, right? And we through a function we map these keys to specific locations in an array. So the function that does this mapping is called hash function. One thing to notice is that ideally we want hash function to be a one-to-one function. So we want every key to be uniquely assigned to like a unique location. However, that's in practice that's very hard to reach. So we end up with something like this. We basically end up with a many-to-one function. So like multiple keys might be mapped to the same location. This is called collision. We're going to talk about that later in this slide. This is another example of a hash function. So like here, let's say like these names are the keys. They go through a hash function. So you see that the key can also be string. It goes through a hash function and then um, assigned to different locations in a hash table. It's the same thing here, the same thing here. So this is like what hashing is all about. And once we assign them locations in the table, so like once we know the locations of the table, if we are searching for a specific key, we go through the same hash function, we find the location, and we go directly to that um, array element or table location, right? So that's like the concept of, that's how the concept of reaching constant time complexity is implemented, right? So this is what we want to achieve. We want to have like keys that goes through a hash function. It gives us a data location, right? And we go directly to that data location instead of searching sequentially or like going through like a structured order. We don't even need to sort the hash table, right? So like it's not meant to be sorted. As mentioned, hashing uses an array table. It just like goes from index 0 to b minus 1. B is the size of the hash table. Each position of the array, some people call it a bucket, right? So a bucket can normally hold only one dictionary pair, right? We'll see that like in one implementation of hashing called chaining. This is not the case. Hashing uses a hash function f that converts each key into an index in the range 0 to b minus 1. So it assigns a location in the table for each of the key values. And every dictionary pair is stored in its home bucket, which is going to be at like the location that the hash function gives us. So you see an example here. So we have pairs of key elements here, and the hash function, let's say like for this case, is key mod 11, right? Let's say it's key mod 11. Okay, if that's the case, we basically know that we can find actually in this one it's not key mod 11, it's some key mod something else, right? Because if it was 11, 22 should be in 0. Anyway, so like we have a certain hash function that maps these data items into different locations in this hash table. Okay, and that's like how this is our hash table, and we have a hash function that does the mapping. Applications of hashing. Compilers use hash tables to keep track of declared variables. A hash table can be used for online spelling checkers. Um, Game playing programs use hash tables to store positions, so to save computation time if the position is encountered again. And hash functions can be used to quickly check for inequality. If two elements hash to different values, they must be different. And it's used for storing sparse data, like it means not dense data. Hash tables are very good if there's a need for many searches in a reasonably stable table. It means like a table that doesn't change that much, like there's not so much deletion, for example, or insertion. Hash tables are not so good if there are many insertions and deletions, or if table traversals are needed. In this case, AVL trees might be better option. If there are more data than available memory, then hash table is not a good solution. Maybe using a B tree, which we didn't talk about this course, but you might see it in your future courses. It might be a better option. But it's also like it's a balanced binary search tree, so it's like similar to AVL in the concept. Also, hashing is very slow for any operations which requires the entries to be sorted. So hash table is not meant to be sorted. So if we need to find the maximum or minimum of all the elements, hashing is not a time efficient solution. And it's not normally used for range searches. So if you want to find items in a certain range, this solution hashing is not very practical, it's not very efficient. For example, finding a record with a key in a certain alphabetical range is not easy to do by hashing. So let's talk now about hash tables. The ideal hash table structure is merely an array of some fixed size containing the items. Okay, and we'll see that like it might also like contain uh, like a pointer to the item, like as we do in chaining. But like in like for now, let's just like see that like the hash table is an array of some fixed size that contains items. A stored item needs to have a data member called key that will be used in computing the index value for the item. Key could be an integer, string, or etc. For example, a name or ID that's part of a large employee structure can be the key for that data element. The size of the array is table size. So this is an array that's like it has a table size, right? So like all the indices go from 0 to table size minus 1. The items that are stored in the hash table are indexed by values from 0 to table size minus 1. Each key is mapped into some number in the range 0 to table size minus 1. And this mapping is done using a function called hash function. Typical hash table operations are initialization, insertion, searching, and deletion. So hash tables are basically collection of pairs, and like through a lookup function known as hash function, this mapping between keys and data locations in the hash table are done. Hash tables are often used to implement associative arrays. Okay, so worst case time for get, insertion, and deletion is order of the size of the table, and the expected time or the average time what we want to reach is constant time complexity is order of 1. The idea for hash table is to divide incoming data into different buckets depending on the value of the data. And the mapping of data value to bucket ID is called a hash function. We need to search just one bucket for particular data. Well, this is the ideal case that we need to search just one bucket. This is what we want to try to reach. So after finding the location of the data through the hash function, we just like go directly there like, to that bucket. If the values are well distributed, or put in a different way, the hash function distributes the data evenly into buckets. The search time naturally, in that case, the search time naturally goes down. So ideally, we want the data that is getting stored in the hash table to be distributed evenly or uniformly. If that's the case, we can reach a faster time complexity. We'll see why this is the case a little bit later in this presentation. The data within a bucket can be organized as a list, often called chaining. So as mentioned, like, we can have the data stored in the elements of the hash table, or the data within a bucket is just like can be the head pointers to different linked lists, right? So that's called like single chaining. We'll see that later in this presentation. So you see like what the hash function is. Here you see that different key values are mapped to different locations in the hash table. And again, I want to emphasize that hash functions are usually many to one function. So many key values can be mapped to the same location. You see that here for K2 and K1, like h, which is our hash function, gives us the same integer, right? This is called collision, right? Ideally, we want to avoid it. In practice, it's not possible most of the time. So it's not possible to have a perfect hashing where like every key value is mapped to a unique um, table element, right? Table location, right? So like this is called hashing. This is like what you see here as well. Hashing is the process of chopping up the key and mixing it up in various ways in order to obtain an index which will be uniformly distributed over the range of indices, hence the hashing. So that's like why the term is like where the term, like the root of the term, comes from. Given a data value, we want to compute an array index. Such a position calculator is referred to as hash function, as mentioned earlier. A hash function maps the search key of a table item into a location that will contain the item, and take an arbitrary integer and map it into an integer that you can use as an array index. We want hash function to be very simple and fast. A simple mod function, modulo function, is often used as the hash map. There are other methods to form a hash function. We'll see like some of them in this presentation, but the most common one is just like a simple mod function. Ideally, two different values should always map to two different indices. This is like zero location. If that's the case, we can reach like direct time access, order of one. It's possible if the value range is small and known. If you know the known the range of all the items, and if that range is very small, this is possible. Often this is not the case. Formally, the value used as the input to the hash function is called the key. Any value is transformed to a natural or integer number key. This also applies to strings, so like your key can be string. A good hash function must be easy to calculate, right, and fast, and it should spread the keys uniformly. We'll also see that like it's gonna be, we will see that a good hash function should be deterministic. It means that it has to give us the same output for the same input all the time, right? It can't be just random. There are different methods to implement hash functions, right? In this presentation, we are mostly gonna focus on the division method, but I introduce briefly some other methods that can be used as a hash function. So the simplest method would be direct accessing or direct addressing. So like our hash function is just like basically the same as our key. So it's as of h of x is equal to x, right? So like you see that 2 is mapped to location 2, 3 is mapped to location 3, 5 is mapped to location 5, 8, and so on. And other elements are not used or null or nil. Direct access tables are ordinary arrays. The keys are in the range 0 to n minus 1, stored in an array of size n. And so like the table array goes from 0 to n minus 1 as well. Item with a key case is stored in tk. So you see that the location of the item, it's going to be its key, right? This facilitate direct addressing. Element whose key is k is obtained by indexing into the kth position of the array. This is only applicable when we can afford to allocate an array with one position for every possible key. So if our set is very small and it's like a very small range, right, this is possible, right? Or like when the universe of key is small, so like when this is small, yeah, this is possible. If that's the case, dictionary operations can be implemented, take order of one time, requires an auxiliary space of on, independent of n. The number of items are stored in the map. Okay, so like 2 goes to 2, doesn't matter like how big the table is, right? 8 goes to index 8, no matter like how big the table is. Direct addressing works well when the range m of key is relatively small, right? Operations of direct access, direct address tables, all are one. So you see like here, like searching, insertion, deletion, like all of them are just basically one operation. But what if the keys are 32-bit integers? Right? If that's the case, our universe of keys are going to be huge. It's going to be huge, right? So in that case, we need to have a very huge array, right? That's not only it takes a lot of memory, but also initializing all the elements of this table is going to take a long time because we have a huge table. So if when our universe of keys is big or is huge, then this is not a practical approach. So direct address tables, like we have like so many entries, like like it's more than 4 billion, and so it takes a lot of memory. And even if memory is not an issue, the time to initialize the elements to nil or null, it's just like might be an issue, right? It might take like a long time to just initialize all the elements of the table. So difficulties with direct addressing: if you use large, storing a table of size u may be impractical. The set key of key actually stored may be small relative to u. So like here, like we might have a huge universe of keys, but like we only have like we're using a small portion of it, but like we end up like with a large array, right? Which we're not use. Most of the elements are going to be empty or null. The more a more frequently used, a more practical approach for implementing hash functions is using division or modulo division. It's like you remember about remainder, the concept of remainder or modulo operator. So this method divides the key by array size and uses remainder for addresses. Okay, so whatever the array size is, we divide the key by that number. So here in this case 307, right? And then whatever the remainder of that operation is, it's going to be the location that we go to for storing or searching or deleting. Algorithm works with any list size, but if list size is a prime number, it provides fewer collisions. So in this algorithm, it's very important to choose a prime size for our table. if we do that, our data, it's gonna be distributed evenly, more evenly, or more uniformly, and this avoids collision. It avoids like having two keys being mapped to the same location. So the address is calculated by this operation, key modulo the list size, the table size. So general formula is like when we have a large number, so like this, where like we are dividing it by a smaller number. Okay, like it's not always the case, but like generally this is like what we have. The table size must be chosen to spread the keys evenly. That's why like we choose a prime number. Uh, so like if you choose a prime number, it can redistribute the table items evenly over all of table and reduces collisions. It's fast because it's just like one operation, since it requires just one division operation. Modular arithmetic process essentially assures that the index is within the specified range, right? When you divide a number by 307, the remainder is always between 0 to 306, right? So like that's the guarantee that we have here. Okay, so why prime? So let's go through an example. So let's say that like we have these numbers or these key values that we want to store in a hash table. Let's once use the table size 10. So like here we are dividing all these numbers by 10 and we are using the remainder as the location for storing these data. So like you see that here many items ended up with location 0. So here this item, this item, this item, this item are all stored, are mapped to location 0 of the table. So this is called collision, right? Many keys are mapped to one location. Okay, if we choose table size as 11 or any other prime number, the chance of collision, it's gonna be smaller or lower. The probability of having collision is going to be lower. So we see that like if we do, if we do that, we divide all these keys by 11 and use the remainder as the key as the location in the table, right? We still have collision here, like we have only one collision though, right? As opposed to here that like we had like 4 items, like 3 collisions basically, right? So this reaches like when we choose a prime number as the table size. Why is this the case? Because real life data tends to have a pattern, and like being a multiple of 11 or any other prime number is usually not that pattern. Okay, a table whose size is some number which has many factor provides the possibility of many indices which are the same. So like but when you choose a prime number as a table size, similar distribution of home buckets is seen in practice when the divisor is a prime. So like you see that it's like more uniform and less collision. Excuse me. Another kind of method for implementing a hash function is like a pseudo-random method. Or like we said, like we cannot use a random function for hashing because the hash function has to be deterministic, right? It has to give us the same output for the same input all the time. And the pseudo-random hashing key is used as seed in pseudo-random number generator, and the random number is called into possible address range using modulo division. In this method, you can just like basically generate a number through a formula right here. Like you see that like here, like here, like this is our key, x is our key, right? And a and c are known values, and y is generated using this formula, and then it's divided by prime number, right? To make it limited to the table, and this is called a pseudo random generation. Or it can be just like through uh, like a fixed list of numbers that you might think it's random, but like you have a um, fixed list, and every time you get like an item in that list. If you remember about like how random number generation works in C++ or in many programming languages, right? This is basically the case. Like we have a list of numbers that are stored in the memory, and if we if we just like basically don't seed it, right? We always go from the first element in that memory location to the next one, to the next one, to the next one. We can also seed it to be random. So like if you don't seed it, like you just like have a sequence of numbers that are stored in the memory. So this is basically mimicking that, right? So we're trying to, in pseudo-random probing, uses a common sequence of random number for inserting and searching. Pseudo-random number generator generates um, the same number of series, same number of series. Sorry for the type. Advantages: eliminates primary clustering. So we'll talk about primary clustering like a little bit later. So basically, it makes sure that the data is um, evenly distributed, right? We don't have a cluster of data in part of the table. Disadvantage is complex and less efficient. Another method is truncation. So truncation is a method in which parts of the key are ignored and the remaining portion becomes the index. So let's say like we have a key that has like, let's say like 7 or 8 digits, and we only like care about the third one or the fourth one, or like only the third and fourth one. For this, we take the given key and produce a hash location by taking portion of the key, truncating the key. It is a good idea if the entire key has some impact on the hash function. Simply truncating a key may lead to many keys returning the same result when hashed, right? So here, like in order to understand this one, like let's say like if these are our key values, right? Hash, mash, bash, trash. And if our truncation function is basically picking the last 3 elements, you see that all of them are mapped to the same location, right? So like this is not a very efficient method, not a very practical method. Another example for this truncation function would be a hash table that can hold 100 entries, and 8-digit numbers is used as key. So we pick the third, fifth, and fifth digits starting from the left of the key as the index in the hash table. So like if this is the key value, right, we use the third, fifth, and seventh location, right? So like this is the index. It's mapped to somewhere in the table, which has 1,000 entries. It's simple and easy to implement, but it might cause clustering. Okay. Another method for hash function is folding. Folding breaks the key into several parts and combines the parts to form an index. So key X, let's say like we have a key value X, is partitioned into parts such that all the parts except possibly the last part are of equal length. What does this mean? Let's go through an example. So like here, let's say like we have a huge number as a key, right? So one folding hash function might be just like separating all or partitioning this into like 3 digits. So 123 would be one number, 203 another one, 241, 112, and then the last one 20, right? So just basically we are partitioning the parts into like smaller parts, and then we just like, let's say like add them to find the location that we want. So this is like one hash function. It's called folding. The parts may be recombined by addition, subtraction, multiplication, and may have to be truncated as well. So like after doing this operation, you might want to truncate it again. Such a process is usually better than truncation by itself, since it produces a better distribution. All of the digits in the key are considered. So like as opposed to this method that we only care about certain digits in the key, here like all the digits are considered using a key and breaking. So like you see like another example here. It was like you see like this operation can be also subtraction or multiplication, and then like let's say like if you do multiplication, then like you can just like do truncation, then just pick the 3 digits from the middle of the number produced. Another hash function is mid square, right? So it's basically computed by squaring the key, the identifier, and it uses appropriate number of bits from the middle of the square, right? So like once you raise key to power 2, right, if you just like convert it to binary, then you just like pick certain number of bits in the middle of the square to obtain the address, the location in the hash table. Middle bits of a square usually depends on all the characters, all the digits. So it is expected that different keys will yield different hash addresses with high probability, even if some of the characters are the same. So it means that like there's a high probability that we don't have many collisions. It's just like it's a little bit difficult, like more difficult than modulo division method to calculate, right? So like there's a lot of process going on here. I'm sorry. So the last method I want to talk about, it's called multiplication method, right? As opposed to division method, we also have multiplication method. So this is the definition for hash function for multiplication method, right? K is our key, right? M and A are numbers that we pick, right? So like it's based on like the hash function that you want to create. So like you know that this symbol is for floor, right, of an item, right? So this is floor again. If you look at this one, this is k times like a number minus the floor of that multiplication. This is going to be always a number, the double number, like a floating number between 0 and 1. A is some real positive constant, right? The value of m is not very critical, right? Typically we choose 2 to power p, right, for easy implementation on computers. And we choose a not too close to 0 or 1. A very good choice given by Dr. Nuth is the inverse of the golden ratio is the square root of 5 minus 1 over 2. So this is like usually the value that is used for A. Because of the relationship of the golden ratio to Fibonacci numbers, this method is also called Fibonacci hashing. Disadvantage is that it's slower than the division method. Like there's like more computation that needs to be done. Advantage, like value of m is not practical. Like we don't need to have like a prime number, for example, for m. So here you see, for example, here, um, here like we want to have, let's say like in this case, k is 123, right? M is 1000. It doesn't have to be 2 to power p, right? That can be 10 to power something, right? So this is 123. M is 1000. A is this number, right? And h of k is calculated like this, and it gives us number 18. So that's the location for this key value to be stored in. The same thing here, right? See, like now key is like has 6 digits. This time is like 10,000. A is the same number as before. It's like the inverse of golden ratio, and this function gives us number 41 as the output, so this is the location in the hash table. There are different methods to use like to implement hash function for string keys, like what we just like saw previously was all like for integer numbers, but you can also like do it for string keys. So what you can do, for example, like find the ASCII value of every character in the string and add them up, and then do division and find the modulo, like the remainder, right? One problem with that would be, so for example, two different strings which have the same characters but in different orders would give us the same value. For example, God and dog, it would give us like the same thing because they have like the same characters. That the position of the characters is not taken into consideration in this formula. One other method that we can have, like it would just like be basically just like find like either the ASCII code or the alphabetical order of the characters of the string and multiply them by their weight, right? Their weight is basically like, let's say like the like the first character is basically going to be multiplied by 1, the second one is going to be multiplied, let's say, by 27, the second one by 27 raised to power 2, and so on. Why like we're using 27 here, like in English alphabet, like we have 26 letters, and like here we also like might have a space or blank, right? So like 26 plus 1, 27. Right, or like you can just like use all letters of a key and so like here like it's basically using just like each character, but like you can also use like here like you see another method, use all letters of a key and multiplier. So like the multiplier this time can be 128, right, instead of 27, right? This like for the sake of faster computation, right? Like multiplying by powers of 2 is going to be faster. And this operation is like very time consuming, right? You see that like we have to do a lot of computation to do uh, uh, to find the location in the table, right, to basically find the value of the hash function. There is a rule, there's a method developed by Horner that it just like makes it easier to compute these polynomials or like these expressions more efficiently. So you see like other methods here. So again, like here, so like we have like if you have a string, you just like might want to choose like only the first character, but this is again like uh, not very efficient because you're going to have lots of collisions. Like any string that starts with the same character would be mapped to the same location. We can just like sum up all these strings, like their like integer value can be ASCII number or their location in the alphabetical table, and then do the mod table size. Like we can just like do weighted sum of these characters, then do mod table size. Among these three, this one is more efficient, right? The 37 slows down the shifting of lower keys, and use like modulo operator if you need to map to a smaller array. So like this is like used to like if our table size is small, right? So like if you need to map to a smaller range. Excuse me. I briefly mentioned about Horner's rule. So Horner's rule is basically a method to calculate or compute a polynomial more efficiently. So let's say if we have this polynomial and we want to find the value of it at x equal to 3, right? This is a very time consuming operation, right? So there's a lot of raising to powers, like multiplication, additions. So Horner's rule provides a structured way of like making this like a little bit easier by factoring, by taking like factor of like x values. So like the number of operations is reduced, right? So this is only for your information. We don't need to go over this. It's just like a mathematical concept. But you see that, like, if we want to, for example, calculate the value of this polynomial at x equal to 3, right? What you can do, just like factor out x in the first 4 terms, right? Again, like, and among these, like, again, factor out another x. Among these two, factor out another x, and then do the replacement of 3 for x, right? So this is basically what the Horner's rule is, like, try to, like, factor out so that, like, the number of multiplication that we have to do is going to be minimized. So choice of hash function is very tricky. So many programmers, like many novice programmers, like, when they need to use a hash function, they just, like, go through, like, reliable sources and find a good hash function, because, like, it's very tricky. Like, it takes a lot of practice, it takes a lot of insight to find a hash function, a good hash function for a certain problem. A good hash function should be deterministic, means, like, it gives us the same output for the same input, should be easy and quick to calculate, it should achieve an even or uniform distribution of key values that occur across the index range supported by the table. Um, if a hashing function groups key values together, right, in a certain part of table, like we have a concentration of data, this is called clustering of the keys. So we should choose a hash function which helps to minimize the number of collisions. Like, we don't want to have, like, many to one mappings, right? So we don't want to have many collisions. Even in the best cases, collisions are practically unavoidable, right? So in practice, for real problems, we have collisions, we just want to reduce the probability of it happening. Perfect hashing is where there are never any collisions. This can be coded when all the records to be stored are known in advance. This is efficient, but design and implementation can be difficult. So, like, most of the time we can't reach perfect hashing. Choosing a good hash function becomes even more complex if we do not know in advance the list of keys to be stored, or if this changes dynamically during execution. So if you have a lot of insertion and deletion. Hash function converts a number from a large into a smaller, a large range into a number from a smaller range, the range of array indices. So there is a rule of thumb for the size of the hash table. Uh, this is like when we are using open addressing. Also, so, like, we're going to talk about that later, but, like, a rule of thumb for size of table or size of array is that we want the table size should be we want the table size to be twice the size of data set. So, like, for example, if you're using division method, we usually want to be, we choose the smallest prime number which is greater than 2s, where s is the number of elements, the number of keys that we have, right? So we're gonna go through some examples, but, like, the table size should be about twice the size of the data set, right? This is a good rule of thumb. If you're using modulo method, like we saw that, like, it's like, very important that choose the table size as a prime number. So, like, then we would have two requirements. One is this rule of thumb, and then the second one would be the prime number. So when we want to analyze the efficiency of hashing, we usually use the average performance as opposed to the worst case scenario, right? Like, we usually use the average or expected performance. And to do this, to, like, be able to analyze different hashing methods, right, we use a factor called load factor. So searching with hash tables is highly dependent on how full the table is, since as the table approaches a full state, more more collisions are possible, like more rehashing are necessary. We talk about rehashing a little bit later, but it's just like basically it gets more difficult to insert new items, or it gets like very time consuming to do searching. So um, the there's a factor, there's a symbol that we use for load factor, which is like the proportion of the table which is full, and so it's basically the ratio between current number of table items over its size, over the table size, right? So basically it just like tells us like how full our table is. The higher the load factor, the slower the retrieval or the searching or inserting. With open addressing, so we're going to talk about like two different methods later on in this presentation, called open addressing and hashing. Single chaining. Single chaining. Open addressing. With open addressing, the load factor cannot exceed 1. Right, because all the items are stored in the table, right? Of course this ratio is gonna be less than 1, right? We always have like less items, less than or equal items in our compared to our table size. With single chaining, the load factor can exceed 1. You might be surprised, like how is this possible? Because in single chaining, as I mentioned earlier, like very briefly, would have like linked list, right? So our table would just like have only the pointer to those linked lists, and those linked lists can just like have like more than one node. So like that's why the load factor can exceed 1. Depending on the load factor, we can choose a better collision resolving strategy. So we'll talk about collision resolving strategies, right? How to avoid collision. To choose a good collision resolving strategy, we have to look at the alpha. We have to look at like how full our table is, right? So we'll see like the reason like we are like going to work with this load factor very frequently in like when we talk about collision. Okay, so now let's talk about strategies for resolving collisions. So this is what collision is: two items, two key values mapped to the same table location, right? This is unavoidable in most cases, right? But we just want to make sure that it doesn't happen very often. Okay, so we're going to look at like some strategies for resolving collisions. A perfect hash function maps each search key into a unique location. It's possible if all the search keys are known and the range is very small. Collisions occur when different elements are mapped to the same cell or same location, same bucket, right? Same slot. Like they're different terms that they're used like for here. Even with a sophisticated hashing function, it is likely that collisions will still occur. So we need a strategy to deal with collisions. There are two main strategies: separate chaining, also known as open hashing, or open addressing, also known as closed hashing. This is like a little bit confusing. This like the terminology is not very well thought through when they designed it. But like open addressing, also known as closed hashing, or separate chaining, also known as open hashing. Like I use like only these two terms, like open addressing and separate chaining. So, but like in other textbooks, you might see these terms. So I just wanted to make sure that you see this as well. We'll talk about separate chaining a little bit later, but this is the concept where we have arrays and linked list concept merged together, use them together. So basically have an array of head pointers. those pointers point to separate linked lists. In open addressing, which is a category of collision resolution scheme that successively examines or probes the hash table until we find an empty or available slot in which to put the key. So like when we have collision, like of course, like here, let's say like if K2 is stored here, if K5 is also mapped to this location, it cannot be stored here, right? There's only space for one item in open addressing, right? So then we basically have to examine or probe through other cells or locations in this table to put K5 in, right? Now this probing can be done in many different ways, right? So we will see that like we have linear, quadratic, or double hashing. These are like all three different probing algorithms that we have. In open addressing, all elements are stored in the table itself. So table should be large. Rule of thumb, it's just like bigger than twice the size of the key values that we have, the key set that we have, like all the items that we have here. Probe sequence, it's just basically the sequence of locations that you examine when you want to insert an item or key into the table, or when you want to search for a specific key value in your table. The delete and retrieve operations must be able to reproduce the same sequence that insert used, right? So like if we're using a certain sequence to insert the items, like for probing, we use a certain probing sequence. For insertion, we have to use the same sequence when we want to delete or search the data or retrieve the data. If the size of the table and the size of the probe step are relatively prime, the probe sequence will visit all the table locations, right? So we want, like, ideally we want to have a probing sequence that would be able to visit all the locations in the table. We'll see that like some of the algorithms that we have for open addressing, in many cases it might have problem doing that, right? It might like end up in a loop and like might miss some of these locations, or it might take like a long time to do all these searches. Because the table size is commonly a prime number, it will be relatively prime to all step sizes. Okay, so like this is like one of these conditions is met here. We have three open addressing schemes: a linear probing sequence, quadratic probing, and double hashing. Okay, we'll talk through all of them in detail. So first, let's look at like the open addressing again, like in general. The idea is to insert if, like when you want to insert, if the cell or slot is full, try another slot until an open slot is found. Like you just like basically probe or search for an open and available slot, like something that's available for insertion. When you want to search, we follow the same sequence of probes as used in insertion, right? When search for an entry and can't look, you can just like look at the hash index, right? So like here, let's say like in this case, if K2 is stored here, right? We might want to store K5 here, right? And then when we want to search for K5, right, we can't just go here. Like it's not going to be direct access anymore, right? We have to go through a probing sequence to find K5. So like here, it takes us two comparisons to find K5. Okay, so when search for an entry can look just at the hash index, you must continue sequentially until find it or and open a spot. Like so means like if the item exists in the table, you find it. If it doesn't exist, like we reach an open cell or open spot. So let me fix this. Sorry about that. Okay, if we reach element with correct key, we'll return it or return true. If we reach a null element, as like empty cell, basically, the element is not in the table, so we return false or like -1, whatever our problem mandates. We store all keys in the hash table itself. Right? This is as opposed to single chaining. Well, the keys are not stored in the hash table. Each slot contains either a key or nil, not in the list. Right? To search for a key, we examine the slot HK first. Right? So what the hash function provides for us, we go to that element. Right? We start the probing from there. And then if that slot contains the key, the search is successful. If it's not, right, if it's not, like we follow a probing sequence, right? We follow a probing sequence, and if we can find it, like the search is successful. If not, if we reach an element that contains not in the list, the search is unsuccessful. There's a third, so like here, like like here, like this is like basically explaining the probing sequence. There's a third possibility: slot HK contains a key that's not K, so compute the index of some other slot based on the probing sequence that we have, and we follow that probing sequence. We do that until either we find the key or until we reach a cell that contains not in the list. It's an empty list, right? So if that's the case, it means that we didn't that it means that K doesn't exist in the table, so the search was unsuccessful. Okay, we'll call this like successful search or unsuccessful search. Right, so a successful search, like we find the element in the table. Unsuccessful search, the element, the key value doesn't exist in the table. The advantage is avoids pointers, so there's no like need for pointers. The memory used is not as bad as the other method called single chaining, so we can use larger table. It's good for fixed sets. We'll see that open addressing would be having lots of problems when we're going to delete data from our table. So if we have a lot of deletion, open addressing might not be a good option. So these two pseudocodes or algorithms basically show you what searching and insertion through hash table is done. So basically here, just like basically we first we search the element that the hash function maps us to, right? If we find it, good, right? If not, like here, like it's using a linear probing, like we go to the next element, we go to the next element until either we find the key that we are looking for, or when we get to the an element that contains not in the list, right? So just keep in mind that was like when we talk about deletion, we'll see that like we have to do some modification to these codes, right? So like here, like like assuming that keys are not deleted from the table. The same thing goes on for insertion, right? We go to the location that hash function provides for us. If that's empty, then that's easy, like we place it there, we're done. Otherwise, like we have to go through a probing sequence. Like here, the sequence used is a linear sequence, right? So like it keeps going until it finds an empty location, or like if our table is full, just like have to have like an exception thrown, like hash table overflow. Or another strategy would be resize the table, which is called rehashing, right? So like if an insertion failed because like our table is full, you have two options, either like saying that, oh, so like I can't do that, throw an exception or an error, or you can rehash. It means like duplicate the size, or like let's say like duplicate or increase the size of your table. And that process is not that easy, as I just said, like duplicating it, like it's not that easy. It's like, you remember I mentioned like the table size should be prime, so like there goes more into it than what I just said. And we'll talk about rehashing at the end of this presentation. Excuse me. So what is the problem with deletion in open addressing? So you remember, like I mentioned, like when we want to search for something, right? We go to that location, right? If that is containing the key value we are looking for, then we are done. If not, we're gonna follow a probing sequence, like let's say like we go to the next one, next one, next one, until we find the key value that we are looking for, right? If we reach an empty slot, it means that the key doesn't exist in the table. Okay, so now the problem with deletion is that we cannot, like if you want to delete um, a location in the table, cannot just turn the slot containing the key we want to delete and make it like contain. No. What if like let's say like here, sorry, what if let's say here, like we had collision and I stored k5 here, right? Because I couldn't store it here, like I stored it here, and later on I decide to delete k2. Right? So I make this one not in the list, or null, or empty, right? Then when I want to look for k5, it's going to go here and it looks for it and it says, oh, it's empty, so k5 doesn't exist in the table. While it does, it's in the next one, right? Because of the collision, we had to store it here, right? But like because of the incorrect way of deletion, right? We might have missed so like we might like missed k5, like we might just like basically disrupt the search process. So if we set the corresponding hash table and enter it to null, then succeeding find or search operations might not work properly. Okay, as I just like mentioned through an example. Recall that for the find algorithm, seeing a null means a target element is not found, but in fact the element might be in a next slot. So a strategy to deal with it, it's called the tombstone, right? So basically, instead of just deleting, right, um, you want to flag that cell. So we use a special value like deleted, like it just like a flag instead of not in the list. So you would have like two basically flags. One, it would just like say it's not in the list. The other one would say like it was in the list, but it's now deleted. Okay, so you just like basically mark a slot as an empty during deletion. Requires a simple flag on the objects stored. This process is also called lazy deleting. So when we search, we should treat deleted as though the slot holds a key that does not match the one being searched for, right? So we still like go through that location. When we want to insert, we should treat deleted as though the slot were empty, so we can insert there. Okay, so that's basically the process that we have to go through when you want to deal with deleting. So the disadvantage is that search time is no longer dependent on alpha, right? So like it just like basically because like if you're basically like even the if the location is not containing any key, it just like basically we still have to go through it, right? We have to like search through it. So like chaining is more common when keys have to be deleted. So open addressing is usually not used when our table goes through lots of changes, goes through lots of deletions. In terms of performance, open addressing in the best case it's going to be order of 1. In the worst case would be the case that like we have to search through the whole, like let's say our table is full and we had like collision, like a big cluster of data. So like we have like in the worst case, all n elements are in one list, right? So like in just like in one sequence, all have the same hash value, right? Let's say like all the keys that we have here got mapped to the um, same location, right? So like we have collisions for K1, K2, K3, K4, K5. So K1 is going to be here, K2 is going to be here, K3 is going to be here, K4 here, K5 here. And if you are searching for K5, we have to start from here and we have to do many comparisons, and it's going to be in the order of n. And the average, suppose there are m buckets and n elements in the table. So n is the number of elements in our key set, and m is the size of our list, our table, sorry. Then the expected list length, okay, it's going to be order of alpha. Alpha is our loading factor, right? So on the average, it's going to be on the order of alpha. Like we're going to go like through like more details about it, like see like the exact values, but like just like keep in mind that if alpha is very small, right? If alpha is a small, then we can reach or like constant time complexity. It's not going to be direct access, right? We still have to go through some like probing sequences, but it's going to be not dependent on n that much, right? So it's going to be almost constant. And the remove performance, in the best case, it's like first element on the list or list is empty, so order 1. The worst case, all elements are on the list, so order of n. The average case, again, right, it's order of alpha. So like if alpha is like small, then it's going to be order of 1. So why don't we always use a well-designed hash table? Like, so these are like depending on, like all of these are depending if we design our hash table very efficiently. So we need to have a well-designed hash function, a well-designed hash table with the right size and everything. So it's not just like as easy as I said, right? Like you have, like there's a lot of consideration goes to it. Why not always use a well-designed hash table? So like basically the disadvantages of open addressing. So like this does not support ordered output, right? So like disadvantages of hash table in general. Hash tables like does not support ordered output because our structure is not sorted. Like it's not easy to find minimum or find maximum. Like we basically have to search through every element. Does not support finding all elements in a given range. If we want to find like all the elements in a certain range, we can do that using hash table. And there's a lot of experience and like knowledge needed to design a very well designed hash function. So like how to design it is not always very clear. Let's go through the first method of open addressing. Okay, so like as I mentioned, the first method is linear probing. So in linear probing, what we do, we basically like you remember that like we just like if you use the division method, like we have a hash function that's usually like the just like a mod operation, right? So so in linear probing, we just add a function of I to the original hash value to resolve the collision. Each table cell inspected is referred to as a probe. Probe sequence is, so in the first probe, in the zeroth probe, we just like go to what h of k provides to us and like mod table size, right? So like whatever this is. The first probe, h of k plus 1 mod table select. So it means that if this location is full, right? If you're doing insertion, if this location is full, we have to go to the next location. How do we find the next location? We just like add I to it. What is I is the probe order, right? So like the next one, we go to the next one basically. If this one is also full, we go to the next one. So this is called linear probing, right? Just like basically add a number to our hash function. The problems is that it has a tendency for clustering um, items in just one location. This is called primary clustering. Any key that hashes into the cluster will require several attempts to resolve collision. So if you have clustering, this is like something that's not desired, because any key that hashes into the cluster, it will require several attempts to resolve collision, right? We have to go through like many different probing sequences, and we'll then add to the cluster um, and just like basically make our cluster like larger. Hence, average search and insertion times increase. So that's why like primary clustering or clustering in general is not desired. And also like we might have adjacent clusters that like merge together. So that's also like very bad. And in linear probing or like in open addressing in general, deletion of records is very difficult, similar for the other open addressing methods. So this basically shows like what like linear probing is. Let's say that we want to insert these items in the hash table. Okay, so the size of our hash table is 11. Okay, right? So 23 mod 11 is 1, so this has to go to 11, to position 1. 18 mod 11 is 7. 29 mod 11 is also 7, right? So like there's a collision here. 28 mod 11 is 6. 39 mod 11 is 6. There's another collision here. 13 mod 11 2. 16 mod 11 5. 42 mod 11 9. 17 mod 11 6. This is also like part of this collision. Okay, so in linear probing, so like if we are inserting the items in the table like this, 23, it's going to go to index 1. Perfect. This is empty, it's going to go here, right? So first of all, like first our table is empty, there's nothing in the list, so 23 is going to go here. The next one, 18, it's going to go to location 7. Initially this is empty, so 18 is going to be stored here. 29 has to be stored in this location, but it's full, right? So according to linear probing, we go to the next available location. So 29 is going to be stored here. 28 has to go to location 6. It goes here. 39 has to also go to location 6, right? So location 6 is full. So we're going to go, so this is the 0th probe. In the first probe, we go to location 7. This is also full, right? So we go to the location 8. This is the second probe. This is also full because we put 29 here, right? So then we go to the next one, and 39 is going to be stored here. 13 mod 11 2, it's going to go here. 16 mod 11 5, it's going to go here. 42 mod 11 is 9, it's going to go here, right? But this is full. So we have, this is the 0th probe. In the first probe, we're gonna store it in location 10. Finally, 17, right? It's supposed to be stored at location 6, so position 6. It's full, 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 full. It just like circles through it, right? And 17 is stored here. So we just wrap around the array. Okay, so like a similar concept we saw through circular arrays. Okay, so you see like what we mean by clustering of data. You see like a huge cluster here, right? Now if I'm looking for, let's say, like number 17, if I'm looking for number 17, ideally I want to have direct access, right? I want to go to location 6 and find 17, but it's not here, right? So then I just like have to go this one, this one, this one, this one, this one, it goes here. uh, this this one I found it, right? So I have to do like 1 2 3 4 5 6 comparisons. Okay, and let's say that I want to search for number let's say 19 in this um, table. Okay, if I want to search for number 19, I have to go through the same hash function, not 19 mod 11 is 8. So I'm expecting 19 to be here if it exists in the list, right? So, but this is not 19, but I can't stop here. I have to follow because 19 might be in the following location. So like this is not 19, 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 this is not 19. I get to an empty location, so I know that 19 doesn't exist in my list. Okay, so that's an unsuccessful search. You see why clustering is bad? Why we want to have uniform distribution? Because like when you have clustering, you have to do a lot of searches, a lot of comparisons. This basically shows that like in the beginning when we insert data, we don't have much collision. As the table gets full, right, we might end up with collisions, primary collisions, and then we also like might end up like having clustering. We might have clustering and collision and then clustering, and we also like have these primary clusters that might merge together, making a huge cluster. So you can see that this works well for an empty table and gets worse as the table fills up. If a bunch of elements hash the same stop, they mess each other up. But worse if a bunch of elements hash the same area, so like this, um, they mess each other up even though the hash function isn't producing lots of collisions. This phenomenon is called primary clustering. I'll leave it up to you to go through these sequences for linear probing and insertion. So these are the items that we want to insert in the table, and this is our hash function, right, which is um, the table size, and like it's 13, right? So like that's our hash function, right? um, so like you see that 18 mod 3 is 5, it's stored here. 41 mod 3 is 2, is stored here. Like we're showing like anything that doesn't need probing, right? It's just like with black arrow. 22 is going to be stored here, right? Then look at 44. 44 mod 13 is also 5. 44 is 3 times 13 plus 5, right? So it has to be uh, in here, like stored here, but this is like already full. So like 44 is going to be stored in the next one, and this goes on like for other elements. And this basically shows you how we might end up like with a cluster. Okay, another example you see here, so like this is used for like it can be also used for characters. So like this is another example. So like here, like again, like we have a table of size 11, we want to insert 12, right? 12 mod 11 is 1, so it has to be stored here. This is full. We go through this one eventually gets stored here. Okay, and if you're searching for 15 later, right, 15 mod 11 is 4, so we go to this location. This is not 15, this is not 15, this is not 15, this is not 15. Get to a empty location, so this is not in the list, right? So it's an unsuccessful search. Okay, you see like why clustering is a bad thing, and you see like what linear probing is. You basically go to the next location, next location, next location. This is the general formula for general code and general pseudocode for searching using linear probing. It's like very easy to implement. I'll leave it up to you to go through it. For insertion also, like this provides the implementation of the function and the pseudocode as well. For open addressing delete, as mentioned earlier, you use the search function to find the item. One simple idea is not to delete but mark, so flag the location. If found, check that items after that also don't hash to the item's position, right? So like we just like want to make sure that like we check this cell deleted. Other elements still are in the right cells. Table can fill with lots of deleted junk. So that's one of the disadvantages of, excuse me, this deleting method. Cells will have three statuses, right? So like it would just like be either occupied, would be empty or not in the list, or might be deleted. Another strategy for deleting is another strategy called eager deletion. So so basically like if once we delete an element, we'll see if the later like we want to make sure the later items hash that position. So we do some shifting, right? If we have a cluster of data and if the next item belongs to that cluster, we just like do some shifting to fill in the hole for later searches. So this basically shows a lazy deletion. So basically if you want to delete 9, right, you go here, 9 mod 11 is 9, we go here, this is not 9, right, so we go to the next one. If this is linear probing, now we found it, right? So what we do, we just like mark it as deleted. So we have like a maybe like a boolean flag that we would turn correct. This shows like the implementation for another method called eager deletion, so which basically like deletes the item and like searches in the later items in the list to see if they belong to that cluster. If that's the case, they shift it so that like we don't lose this memory location. I leave it up to you to go through this one. But I just like show you like for example how this is done. If this is the original table that we have, if we delete 0, so just like basically this like first this is deleted, right? Like in the tombstone or lazy deletion, you would just like mark this as deleted. But then we also search like in eager deletion, we search cluster for pairs. Like we want to see like, okay, if like 45 belongs like here, like we had a cluster, we want to know like if they belong to the same sequence, right? So if that's the case, so like here, like 45 mod 11, sorry, mod 17 is 45 mod 17 is 11, right? Because 45 is 2 times 17, which is 34 plus 11. So 45 belongs to here. Why is it not here? It's because like of clustering, right? So because of like collision, right? So like it just like goes here, 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 and got stored here. So yeah, 45 belongs to this cluster, right? So that's why like we check this. If it belongs, then we switch it here so that we don't lose this memory space. Another one, delete 29. Again, 29 mod 17 is 12, right? So 29 was supposed to be here, okay, but it's here because of the collision. So we delete this one. Now we want to see if 11 belongs here, right? 11 mod 17 is 11, so 11 was supposed to be here. Why is it here? It's because of collision, like because of linear probing, we just like put here, right? So like now we can shift this one here. We do the same thing for 30, we do the same thing for 33, we do the same thing for 34, 0, and 45. See, like deletion, if you want to like be very memory efficient, this is not like gonna be like, it's gonna be a very time consuming process. So it's not done for tables that have to go through like lots of deletions. For tables that are not very stable, we try not to use linear probing. This shows again the same thing for 34. So it's again like a trade-off for memory and memory space and speed, right? So like here we want to save our memory. This is gonna slow down our process, right? We have to do a lot of shifting to make sure that we save this memory. We want to see like the performance of linear probing based on the load factor of the table. In the worst case, right, when we have like let's say like a huge cluster that like occupies the whole table, find, insert, and delete our order of n. N is the number of pairs in the table. For any alpha less than 1, right, for any alpha less than 1, if the load factor is less than 1, it means like if the table is not full, the linear probing will find an empty slot, right? So there's like, it just like basically searches through the slots sequentially, and it will definitely find an empty slot. Hashing efficiency for a search also depends on whether the search is successful or not. So like in analyzing efficiency of hashing, we usually like have two different cases. So for successful searches and unsuccessful searches. So here, like based on like complicated math that we are not gonna follow, like not gonna like study in this course, we're just gonna trust the final results. So the expected or approximate average number of probes or comparisons for a large table size for a successful search, it's going to be 1/2, 1 plus 1 over 1 minus alpha. And for unsuccessful search, it's going to be given here. Okay. So like you can basically like approximately find out how many searches you have to go through depending on your alpha, like how many probing sequences you're going to have, like depending on your alpha. And it's different for successful searches compared to unsuccessful searches. So for example, if your alpha is 0.5, for a successful search, on the average you have to go through 1.5 probing sequences. You have to go through 1.5 probes on the average. For unsuccessful, it's going to be 2.5 probes. As alpha increases, so when alpha gets bigger than half, 0.5, you see that the numbers are gonna increase drastically. So if alpha is 0.75, you have to go on the average 2.5 probes for a successful search and 8.5 for unsuccessful. And like if table is almost full, if alpha is 0.9, this is successful probes are going to be 5.5 on the average, and unsuccessful probes are going to be 50.5 on the average, right? And you remember like as you do insertion, alpha is going to change, right? So like alpha is like it's going to change like as you do insertion, because like your table gets fuller. The second open addressing method is quadratic probing. So like one problem that we saw with linear probing was primary clustering. That would just like all data would be in one big cluster. We'll have a concentration of data in one cluster. So in quadratic probing, searches the hash table beginning at the original location specified by the hash function and continuing at increments of oh, sorry about that. It's just like 1 raised to power 2, 2 raised to power 2, 3 raised to power 2, and so on. Okay, so the probing sequence, as opposed to linear probing, which was f of I is equal to I, is now f of I is equal to I squared, right? So in the first one, right, in the first probe, 0th probe, right, we just like go to the location that the hash function provides to us. If it's full, right, then we go to the next one, because it's like 1 squared is 1. If this one is full, we're just gonna go to that location plus 4. It's like 2 to power 2 for the second probe, and so on for the third one, like 9th location after what the hash function gave us, right? And this continues. So in this case, we do not know if it this quadratic probing, it probes all the positions in the table, right? We say that for linear probing, we make sure that like it probes all the elements in the table. That's not the case for quadratic probing, but it's less likely to encounter primary clustering, but can suffer from another thing called secondary clustering. Secondary clustering, it means that like if two key values would end up having the same probing sequence. If two values have the same initial probe position, then their pair sequences, then their probe sequences are going to be the same. So like we just like have the same probing sequence. Okay. So here, like if you want to insert 12, right? If you want to insert 12, like 12 mod 11, this is our hash function, is 1, right? So we should be inserting it here. If we were using linear probing, we wouldn't, like we would check this one, then this one, then this one, and then insert it here. But now we're using quadratic probing. So 12 mod 1 is 11, we go here, this is 4. The next one is gonna be 1 plus 1 squared, which is 2. So we check this one, this is also 4, right? So like and then the next one, it's just gonna be like here. So like we I think there might be a problem here, because like 1, so like, okay, sorry, this is not the case. Sorry, 1 plus the second one, it's gonna be 1 plus 4, so it's gonna be fifth one. Like this is again 4, right? So like you can't do this. The next one, it's gonna be 1 plus 9, which is 10, right? This is again 4, right? And then the next one, it's gonna be 1 plus 16, which is gonna be 17, right? So it's gonna be 1, 2, 3, 4, 5, 6, 7. Again, like we check this one, this is also 4, right? We just, like you see, like it's a circular array, right? So we circle through it. So it basically checks all of this, like this is also 4. So the next one is going to be 1 plus 25, which is 26, right? So here we have 11, so like it's going to be 1 plus 26. So eventually, like if this is 11, it's 22, so it's eventually it's going to come here. It's like there are 22 here, and then plus 4, 26, so it's going to place it here after all these many probes. First we started from here, then we went here, then we went here, then we went here, then we went here, and eventually went here. Okay, so that's how quadratic probing works. Okay, so I'll leave it up to you to do this example. It's an example for you to see like how this is done, how to insert, right? So like for example, this one 4D mod 7.5, this is empty, so we'll place it here. But for this one 48 mod 7 is 6, right? So this is full, right? Where should it go? So if this is full, this is for the 0th probe. The first probe is going to be 6 plus 1, but we don't have 6 plus 1. So it's going to be 6 plus 1 mod the size of the table. So like it's going to be 0. So it's going to go here. And the next thing, and so on. So like I'll leave it up to you to fill out this table. If size is prime and alpha less than half, if the table size is prime and alpha, the load factor, is less than half, then quadratic probing will find an empty slot in this many probes or fewer. Okay, so in size less than size over 2 probes or fewer. Quadratic probing usually does not suffer from primary clustering, but it might suffer from another clustering called secondary clustering, right? When like two keys end up having the same, if two keys have the same initial probe position, then their probe sequences are going to be the same. Okay, multiple keys hashed to the same spot all follow the same probe sequence. If the table is not primed, then like this problem is going to get much worse. The number of alternative locations can be very reduced, severely reduced, since the hash port position is a value mod the table size. So for example, if our table size is 16, you see that like 1 mod 16 is 1, and 4 mod 16 is 4, 9 mod 16 is 9, 16 mod 16 0, 25 minus 69, 30 minus 36 mods 16 4, and so on. You see, like we get 1 4 9 0. That's it. And again, 1 1 4 and 9 is basically repeated many times. So like the number of options that we have for locations is severely reduced. For quadratic probing, the average number of comparisons for successful search is natural log of 1 minus alpha over alpha, like the negative of that. And for an unsuccessful search, it's going to be 1 over 1 minus alpha. So like again, you can calculate like how, like on the average, how many comparisons you have to make depending on the on how full your table is for both successful and unsuccessful searches. It requires fewer comparisons than linear probing. In general, it requires fewer comparisons than linear probing. The last open addressing method I'm going to talk about, it's double hashing. So here, like we basically use an auxiliary hash function, like for collision, only for the sake of collision. So in this case, we have like our original hash function. We would have like another one, let's call it G, right? It's a second hash function, and this is going to give us the probing sequence for when the collision happens. So if we, so h of k provides us the first location, right? If that is like empty, like we insert the data there, that's going to be in the 0th probe. If it's not, to find the probing sequence, we use a secondary hash function, so g of k. So then like that basically this is going to give us the next location, and then like just multiples of that is going to give us like the next probes. So the requirements is that h2 of any key is not 0, because like we're supposed to like provide a different value than h1, right? And h2 and h1 are not the same, to avoid secondary clustering. And the value of the second hash function h2 of k must be relatively prime to the table size m. Okay, so a good choice for this, I'm sorry, like for like not having consistency, sometimes I call it h2, sometimes call it g. A good choice for this second hash function is to choose a prime number r, which is smaller than our table size, and let this second hash function to be r minus k mod r. You see an example here. So like here, like our table size is 11, so our h1 is key mod 11, our h2 is 7, this is r, a table like a prime number, minus key mod 7. So this basically makes sure to clustering is less probable. Double hashing is safe for alpha less than 1 and does not suffer from clustering problem. Okay, so I'll leave it up to you to go through this example. So like again, like if you want to place 76 here, 76 mod 7, it's going to be 6, so it's going to go here. Then 93 mod 7, it's going to be 2, it's going to go here, no collision, right? So like it's going to go here. 4D mod 7, it's going to be 5, again like no collision. 47 mod 7, it's 5, right? So like here, like then we have collision. Okay, so here the 0th probe is filled, right? So to find the next sequence, we just like put 47 here. 47 mod 5, it's going to be 2. 5 minus 2 is 3, so we go 1 2 3, 47 is placed here. Okay, next one, 10 mod 7 is 3, it's going to go here. 55 mod 7 is 6, right? So 6 is full, right? So this is the 0th probe. Then we just like have to basically calculate 55 mod 5. It's 0. 5 minus 0 is 5, so we go from here, sorry, from here it's gonna go, where did we start? 55 mod 7 was 6, right? So we started from here, go 1 2 3 4 5, it actually goes here. 55 is going to be stored here. Okay, so that's basically what it is. Another example you see for double hashing, oh, this one I solved the other one for you, so like I'll leave this one up to you to verify this. Another example here, again, like here, like if we have the same example that we did using linear hashing and linear probing and double probing, now like we're doing using double hashing, right? So we want to insert 12 here. Your h1 is like x mod 11 and your h2 is 7 minus x mod 7. So please go through it to see like how these probing sequences are searched through to find a location for 12. For double hashing, the performance in terms of formula, it's almost the same as the quadratic probing, right? So double hashing is one of the best methods for dealing with collisions, though. Its average it's like a typo here. Its average performance is similar to double hashing, but does not suffer from secondary clustering. Now, we'll see another category of collision resolution, right? So dealing with collision. So this is called single chaining. So like this is like where like our table doesn't contain the key values. It just has pointers to head of linked lists, different linked lists. So like these are basically our buckets have like addresses of linked lists. So we put all the elements that hash to the same slot in a linked list. The slot contains a pointer to the head of the linked list. The idea of chaining is to combine the linked list and hash table to solve the overflow or the collision problem. Okay. Each table position is a linked list. The cell can contain a pointer to a linked list of data insertions. Right, so like we call this like each of these locations, we can call it as a bucket. We add the key and entries anywhere in the list. It would be much easier to just insert it at the front, which is like much faster. So we usually insert it at the front. You see, like in hashing or hash tables, we don't care about like order, right? We're not trying to have like a sorted or ordered structure. So we can just insert it anywhere, like it's easier to insert it at the front. Advantages over open addressing, it's simpler and faster insertion and removal. So like here, like removal is easy, right? Like we don't have the problem that we had with removal for open addressing. The insertion is also very fast, right? Like we don't have to deal with collision, like we don't have to go through like different probes, like we just like basically insert here, like the front of the linked list. It's dynamic, naturally resizable, allows a varying number of records to be stored, but should still minimize collisions. So in this case, make the table size roughly equal to expected number of keys and entries. Okay, so um, like for single chaining and open addressing, we have different rule of thumb. Like here in this case, like we make table size roughly equal to the expected number of keys and entries. If you remember, for open addressing, we mentioned that like we want it to be at least twice the size, um, and it should be a prime number. But like here, like we don't have that. Like we just like we want to make sure to minimize the memory. No clustering events, since never still another hash values spot. Deletion is immediate, don't need to mark the spot. Disadvantage, okay, memory overhead is very large, right? So like it has a lot of pointers, right? So like it's more complex to implement, and we have a linked list at every element in the array, right? So like it just like have a lot of memory locations. Here you see like some examples of chaining, right? So like how insertion of these items into the hash table is done. I just gonna, sorry. Um, so like for 3 different examples, this is one example, this is another example, this is another example. You see like how this is done. You see like here, like how the insertion is done at the front of the linked list. The operations that we have are insertion, searching, and deletion, similar to what we mentioned about hash table. So insertion, it's just gonna be just like changing the pointers, like allocating a new memory location and having this pointer pointing to this new memory location, and eventually breaking this link and like providing a new link and another link here. So this shows you how the insertion works. It's basically the same as like doing a search, finding the slot, like finding the bucket, and then it's just like basically inserting a node at the beginning of a linked list, which we have done like many times. It's going to be the same for deletion, right? So like you just like find the point, like then like you go through, like you traverse through the linked list, you find the item and delete it. For searching, it's also like similar. You just like basically first you go through the hash function, you find the bucket, right? You find the table location, then you traverse through the linked list to find to find your key value. If it exists, then you just return it, or return true. If it doesn't exist, you return false. And the deletion works the same way. Like once you just like go to the memory location, like you have the head pointer of the linked list, you traverse through the linked list, and if you need, you delete it. If you find it, you delete it. So like this also shows like a general overview of how to implement chaining. Like we would have like a structure or class for our nodes, would also have a class for our hash tables, right? So then like we would have like all those member functions that we want to have: insertion, deletion, and searching, and like maybe like is empty, is full, other things that we want to have for dictionary or a table, hash table. Expected performance. um, so if we have m buckets and n elements stored in the hash table, like the load factor is alpha. It's alpha is bigger than 1. So insertion operation is order of 1, because we just like gonna insert it at the beginning of the, you see like here, right? This is gonna be order of 1. Like our hash function is order of 1. Like we go here, and like these are like some limited number of comparisons, like limited number of operations. So it's order of 1. We don't do like searching or probing. Search and delete operations require a traversal through the linked list, right? So like this depends on how well distributed the items are. right? So like if all of them end up in the same bucket, in the same linked list, that's the worst case scenario, right? If we have a relatively well distributed hash table, then we would have the average case. So in the worst case, if all keys hash into the same bucket, we have n single linked list, then we have like order of n plus time to compute the hash function. In the average case, keys are uniformly distributed into buckets. Any given element is equally likely to hash into any of the m buckets independently of where any other elements has hashed to, right? So we don't have like the collision problem that we had in open addressing and like probing sequence, right? Um, and the clustering of data. Um, so for a successful search, on the average, it would take 1 plus alpha over 2 comparisons. For an unsuccessful search, on the average, it takes alpha comparisons. Okay, so that's for single chaining. We have another concept called rehashing. When the table gets too full, especially in uh, open addressing, the average search time deteriorates from order of 1 to order of n. So we can just create a larger table and rehash all the elements into the new table. Usually like when the table gets more than half full, like you might want to do that. Or when an insertion fails, like when like you can't like insert an item, like using linear probing or quadratic. Let's say like you're using quadratic probing and like you can't do insertion. So is it as simple as doubling the size of the array? No, because like we want the size of the hash table to be prime. Is it just like as simple as copying the items from the original hash to the new hash? Again, it's not, because our hash, like if our table size is going to be different, our hash function is going to be different, right? Let's say like our original hash table was size was 11, right? If we want to hash it, it's going to be like 23, right? Then our original hash function was mod 11, now it's going to be mod 23. So like everything is going to be different. Running time, it's going to be order of n, right? But it's infrequent, like we don't do rehashing like all the time, right? It's not like a very secure process for applications that like need like a lot of safety or cyber safety, data safety. This compares the number of probes for linear probing, double hashing, and chaining, right? Quadratic probing is very similar to this as well, but it basically shows you how the number of probes increase for different methods as alpha increases. See, like if alpha is small, right, like it might like not make a lot of difference which method to use, right? But as alpha gets bigger, right, chaining it's going to be more efficient, right? And you see that here for chaining, like alpha can be bigger than 1 as well, because like our like data is not stored in the table, right? It's stored in the linked lists. Okay. So when half full, the techniques are nearly equal in efficiency. As the table fills, chaining is the most efficient. So you see like here, like shows like comparisons for successful and unsuccessful searches for all these different methods. While separate chaining is the most time efficient collision resolution scheme, you do have the storage overhead of the pointers in the linked list. If the records are large, the addition of a pointer is insignificant. So separate chaining is a good choice. So again, like it's a compromise between speed and memory. This shows you like a like a like a like a declaration basically for like a hash table class, right? So like you can define your own class, hash table class, but this basically shows you like some of the functions that you might want to have: insertion, removal, assignment operator, like clearing the whole thing, like searching. You might want to have like constructors, copy constructors, and so on, destructor, and so on. We didn't talk about like other topics that are related to hashing, or like we didn't talk a lot about some of them, like dictionary and map abstract data types are like two the abstract data types that we didn't talk about very like in depth in this lecture. Hash list and hash tree, random probing, or pseudo random probing, universal hashing, birthday paradox, Horner's rule, perfect hashing, two-level hashing table, and different hashing function methods. Like we mainly focused on the division one, like we then focus on the different hashing function methods. So these are things that you can study on your own time. Thank you so much. Sorry that this lecture was too long. I hope you have a nice time. Take care.